discussion on what data is and how we describe data specifically. And so in this lecture, we're going to focus on the numerical measures that are used to describe a data set. And so a lot of times we use this in terms of this idea of the central tendency of our data set. And so your mean, and your median are very much central tendency values. Mode is going to be your most common value. Weighted mean and geometric mean are also types of central tendency data points. And then your percentiles and your quartiles, you might have most commonly be familiar with those values in terms of your standing or your rank in your graduating class. And so remember, when we're looking at a value for every possible observation, we're looking at population parameters. But if we're just using the values to describe the sample that we've collected, we're looking at those in terms of sample parameters. And so population mean and sample mean are basically determined the same way. You add up all your observations and you divide by the number of observations that you have. When we're looking in terms of the population, we're going to be using the value mu. And when we're talking about a sample, we're looking at the value of x bar. And so once again, the capital N will be looking at something describing your population, and lowercase n represents the way we describe just the sample that we're looking at. Median is that exact middle value. So when you take all your data points and you rank them in order from highest to lowest or lowest to highest, this is the observations that's going to be right in the middle. And so this is not going to be really influenced by extreme values. And so sometimes, for example, if you're looking at somebody throwing the curve because they had such a high grade, that's if they make the curve based on the median values, then that one student acing the exam when everybody else did poorly isn't going to make a difference. Your mode is going to be your most commonly observed data point, and so you can have a set of observations that have the exact same value. So we could have the same number of observations for smell nice as we have for far out. But in here, we only have one category that had the largest value of observations. But we can then look at our mean, our median, and mode and use it to describe how our data is shaped. So if our mean, our median, and mode are exactly the same, the distribution of our observations should fall within this shape in a symmetrical manner. But if we start seeing the average being really low, but our mode is pretty high, this tells us that we're going to have a lot of outliers, predominantly a lot of those a positive skewed distribution. You'll see a negatively skewed distribution when you start seeing your median and mode not being very close again, and your mean being so much higher than the others. That's going to end up giving you, once again, indication that you have some outliers in your data, or maybe not a symmetrical distribution of your data. Your weighted mean is what you're probably commonly familiar doing within maybe a class that has you average all of your project scores and weight them at 20%, and then take all of your exam scores and weight those at 80%. So it's the same concept where you take the number of hours each type of employee worked multiplied by the unique hourly rate for those employees, adding that up and dividing by your total number of employees to get your average hourly rate for this set of employees who worked these hours at these different pay rates. Your geometric mean is really an nth root of your positive n values. It can be used when you're trying to look at the rate of change from one period to another. So a lot of you might be asking, why do I care about this dispersion? So we're going to be looking at our range, trying to find what's that difference between my highest value and my lowest value? And so this is going to tell me that spread of my data points. For example, if you're looking at it from a science background, you might be thinking about how reproducible are my results going to be. If I have a huge dispersion in that, I'm going to maybe be more skeptical of that average value that you report being a really good or useful value in statistical inferences later on. And so when we're looking at that range is also influenced by what we call our variance. So your variance is looking at the difference from each individual observation from the mean. So the difference of each observation from the mean and squared, so that you don't have a negative value. And if you're looking at a set of data that's a sample, you'll use n-1. And if it's for a population, you'll use capital M. And that's going to be based on whether or not you need to have a certain number of degrees of freedom based on the statistical inferences that you plan on making. And so basically it's the average of how far away each observation is from the mean. And so when you take the square root of that, you get what we call the standard deviation. And so this is going to tell you basically if you have plus or minus a standard deviation of plus or minus 5 grade points, that means on average, most of the students are going to have scored within plus or minus 5 points of your average score. Now, if your standard deviation were maybe 10, then you see once again that you have a much wider range in your data that you're seeing in your data collection. And so one of the things that we do is we look at your z-scores. We look at how many standard deviations is your observation going to be from the mean. And so if I said that we had an average exam score of 85 plus or minus 5, then if you had a value inside of that, we can then figure out how many standard deviations that is. And so you would take your exam score minus that 80 divided by our 5, and you'd figure out what your z-score was and what was the probability that you would have gotten that score. And so some ways that we can interpret the use of standard deviation is by using Chebyshev's theorem, which requires that our z is greater than 1. So you're more than 1 standard deviation away from your mean. And so when you're looking at this, you're going to expect that 75% of your data values are going to be within z equals 2 standard deviations. 89% of your data points should be within 3 standard deviations. And if your 4 standard deviations, that should encompass 94% of your data values. So if you find that your exam score was multiple z values away from the mean, that's going to be an indication that your exam score was becoming more and more different from the group that took that exam with you. We also look at this in terms of the empirical rule, and they kind of define it a little bit differently, but 1 standard deviation plus or minus 1 standard deviation is 68%, plus or minus 2 is 95%, and plus or minus 3 standard deviations is 99.7%. So the greater that z-score value is, the greater likelihood that that observation is an outlier. And so oftentimes you might evaluate an observation to see if it is an outlier, and you maybe might want to collect more data, is by determining what the z-score is for that observation. And so here you can calculate the standard deviation of grouped data. Here we have the frequency of observations between each of these different profit categories with our midpoints. And then we find our midpoint subtracted from our means. Then we square that value, and then we of course multiply it by the frequency again to find that our standard deviation for our group data is 652.33 observations.